We are.
All right, thank you. Welcome everyone to this final presentation from Omdema and HOT Humanitarian OpenStreetMap. It's a project run by 50 participants over 12 time zones, and it's particularly aimed at an AI-assisted collaborative mapping tool for humanitarian aid. And as I said, this is the final presentation. So I'm very excited to go over the outline here. First, we start with an introduction on the project, going over an exploitation phase, have the model selection because we are selecting several models to do the footprint extraction for buildings to assist humanitarian actions in when there's a disaster, so disaster aid. How did we develop that will be explained. Ultimately, we went to package to streamline the production of those footprints, and we will demonstrate how the whole pipeline is working, and then I will come back to conclude the project and have a question and answer session. So without further ado, because we have a very packed agenda, I will hand over to Basel, who will tell more about the project.
Hello, I hope everyone is doing well. So in this project, we're building an AI mapping tool where models can be created and trained by end users in a live environment. So training data sets are created and stored in a certain environments, and the mappers will use the tool to build AI models using the training data. We built this tool for HOT, which is an international team dedicated to humanitarian action and community development through open mapping. So we will first go over the problem statement, and then we'll introduce the solution. And after that, we'll introduce the method used to develop the solution. Can you please go to the next slide? So for the project lead, we had Guy van den Doel. For the task leads, we had Tassine Hoek, myself, and Arno Roder. Our client, as I've mentioned, is HOT, which is short for a humanitarian OpenStreetMap team. And for the contributors, we had 50 machine learning engineers from over 12 time zones globally. Today, the presenters are myself, Michael Adiere, Tassine Hoek, and Shaima Higazi. So, as I've mentioned, we in this challenge we were trying to build an open source AI assisted mapping tool, and one might ask himself, why is this actually important? So, why would one use artificial intelligence to do mapping from aerial images? So one obvious reason is actually to make sense of the chaos in case of natural disasters, and to thus plan the best response to save lives and to minimize the suffering. And another reason is that having an AI mapping tool will help actually in reducing the time to do the actual mapping to extract the building footprints. Can you please go to the next slide? So our project goal is to actually have a system in which the mapper can select a region or an area of interest. And after the mapper selects this region, a training data set will be created and saved in the corresponding location. And the mapper will get the chance to train a semantic segmentation model on the data extracted or selected, and the model will detect the buildings, and from the segmentation maps that we'll obtain, will be able to extract the building footprints. So it's important to note that the mapper only selects a specific region in the area, not the entire area, and the model will be used to extract the buildings for the whole area of interest. Can you please go to the next slide? So we had four components of our project. We first had the pre-processing stage, in which we rasterized the given images, and then we trained the model on the rasterized images. We performed inference with the model trained, and we finally did pre-processing to extract the building footprints from the segmentation maps obtained. So we tested a variety of machine learning and deep learning models for this project. Can you please go to the next slide? We first developed this approach in which we assumed that we have an available pre-trained model, and we mentioned that we must utilize transfer learning as the amount of the data provided is a little is small. So we had to find a pre-trained model that is preferably pre-trained on aerial imagery like the OpenCities model or the RAMP model. And after we load this model, we fine-tune it on the separate created data sets for the separate regions. And thus we obtain a model for each region. And in case one of these models or one of the pre-trained models didn't perform as expected, as expected, I mean whether it has a high inference time or it didn't achieve the actual threshold of the intersection over union score, we developed another pipeline in which we train the model from scratch and then we fine-tune it. So the difference between this approach and the previous approach is to simply train the model from scratch instead of using a pre-trained model. So we trained for the models trained, we trained a UNet model with a ResNet backbone pre-trained on the ImageNet dataset and loaded it from the semantic segmentation library. We also built a baseline CNN encoder decoder. We tried the traditional ML algorithms for pixel-wise classification by first extracting the features using VGG that was pre-trained also on ImageNet. And finally, we tried the RAMP model, which a UNet model with an efficient net encoder, which is pre-trained on large amounts of aerial imagery. So for the model selection, we selected the RAMP model as it was the best performing model. So the RAMP model stands for a replicable AI for microplanning. As I mentioned, it uses an efficient net encoder as it's a UNet model that uses an efficient net encoder as its backbone, and it was trained on large amounts of aerial imagery. It was trained on about 80 gigabytes of data, and it's open source, and it enables users to build their own deep learning models for their region of interest. So the user just have to do the fine-tuning. And for the development, I leave the ground for Michael. He'll take it from here. Michael.
Hello, I'm Michael. I'll be presenting the parts for the process and result development phase of this project, where the process was destined and the result of each process. Next slide, please. So the first step of this project is preprocessing, which is basically preparing of the data set from 5 regions provided by HOT. The first step of this process is georeferencing of the aerial images, the tile images, which entails converting the X, Y, and zoom values of each tiles to WGS84. Then after it is converted to WebMeca or EPSG 3857. After that, we proceeded by fixing of self-intersecting polygons, which are just building edges that cross across each other. After which we projected the GeoJSON data to match with the tile EPSG 3857. After that, we went ahead by clipping and rasterizing of each building footprint. The next slide, please. So the result of the preprocessing step can be found here. By the left-hand side, we can discover that there is an image tile image of the buildings and a corresponding label, which is rasterized beside it. By the right side of this display, you can discover that there is a clip GeoJSON label using a bounding box, which are the result of the processing step. Next slide, please. So after processing the data, we move forward by training, which is basically fine-tuning of a pre-trained machine learning model introduced by Professor Bezel. We utilize the RAMP model as explained by him, which is an acronym for replicable array for microplanning, which utilizes an efficient unit for encoder components, which actually plays a role in increasing the accuracy of this model because it's increased performance by compound scaling of parameters such as height, width of these image tiles. Now, this model has been pre-trained on a large data set of high-resolution satellite imagery from SpaceNet. After we fine-tune this machine learning model to work with our data sets, we save the model checkpoints for prediction of unseen data in the future. So it can be discovered that we have an average accuracy of 93.5%, which is quite high, and an average intersection over union, which is IOU, of 83.6% across all regions. Next slide, please. So these are the metrics obtained from the training step. It can be observed from the test of 5 regions, we can observe that from region 1, we have 98.7%, region 2, 92.3% accuracy. Region 3, we have 93.5%, 4, 96.6%, and 5, 86.6%. It can also be observed that the mean IOU, which is basically a metric for segmentation model, has a minimum of 72.6% in region 5 and 90.1%. We can also visualize metrics like the batch size, number of epochs, inference time from these data sets. Next slide, please. So after processing and training of the model, we move forward by inference, which is basically prediction of unseen data, unseen image tiles on the model checkpoints that were set previously in the training step. It is done by iteratively predicting test data and taking the model predictions in batches, after which the conversion of probabilities of these batches are done to binary values and saving in PNG format. After that has been done, we move forward by georeferencing of the PNG images using the input style image data like the process step, which are basically the X, Y, and zoom value of each tile. Next slide, please. So these are the results from the inference stage from various style data. Though it can be discovered that the machine learning model performed quite well, but it still needs some processing before we move forward to vectorize or to polygonize this model, these predictions to work with the AI model. Yeah, next slide, please. So now these are merged masks stitched together on each region. These are basically the predicted tiles from the inference section, stitched and superimposed on the buildings in these 2 regions. So this is basically a bringing together of each image prediction. Next slide, please. So the last step of this main process is the post-processing, which is basically, like I explained previously, after this data has been inferred, the new and unseen data has been inferred, it needs to be processed. So these are made in 2 methods. The first, which is vectorized, which is a polygonization utility created from scratch using scripts and libraries, and polygonize, which is also a polygonization utility based on AutoBFE processing. This is actually a toolkit, and AutoBFE stands for Automatic Building Feature Extraction, which is a toolkit made by AutoBFE. Yeah, next slide, please. So these are the results of the post-processing. The left, which is vectorized, the predicted mask has been placed on buildings, vectorization and polygonization. Yeah, next slide, please. So the deliverable of these 4 processes has been merged into a package by the team, into a single package, launched into or published into PyPI from pre-processing, training, inference, and post-processing, which would be introduced by the next speaker. Next slide, please. So I would like to hand over the mic to Tassin, which will be putting us through the virtual environment and the coding environment of this project. Yeah.
Tassin,
Tassin.
I will stop sharing. You can bring your screen up. Yeah, there we
So
go.
this is the repo that holds all the code about the environment that is. In order to install this package called hot, we need to prepare a special type of environment that will contain some specific packages like GeoPandas and GDAL, I think. So during testing, we found that if we're doing this kind of things locally, then the package handling is quite complex and it might fail from time to time. So we had to like install some packages from Conda and then some other from pip. And in that way, the code worked perfectly. And we have documented all the steps that you could take to produce the exact environment that we tested in. Like we have provided an environment file in YAML format, and using that file, you can create an environment, Conda environment. And if you want to create that environment from scratch without any kind of environment file, we have that steps also. So whatever you prefer, you can do that. So I will give a demonstration of how you can pre-process the data. So from hot, we will get like this. So there will be PNG images of satellite, satellite images, and there will be labels. The labels will contain the building geometries, the building shapes that we need to rasterize in the pre-processing step, because for the model training part, we need both the satellite images and the rasterized label, which means a label in PNG format or TIF format, whatever, that will contain like black and white pixels indicating whether there is a building or not. So the buildings must be indicated in that way. So I'm going to demonstrate this pre-processing. We just call the pre-process function available in the package hotlib. We need to specify where the input path is. And by input path, we are implying a folder that will contain the PNG images and the GeoJSON labels file for the entire region. And I need to specify where the output data will go. By output, I mean we can do a lot of things, but at the very least, we need to output the clipped labels. So for each of the regions, for each of the tiles, we need to clip the whole buildings labels for that region. I think I will give an example later. So there are some options, like we can specify that we need the final labels in like image form. It will by default come in GeoJSON form. Then we can also specify whether we want the final rasterized image for like 0:1 format. That would be fed to the model, but we won't be able to like verify our pre-processing by looking at that. Whatever. Let me check. So I'm running this script. As I have like enabled all options, it will first georeference the input tiles that are in PNG format so that we can check it in a software like QGIS. Then it clips all the labels for each of the individual tiles. So the output is in output v2 folder. The reference images are in the chips folder. It's actually as part of the requirement from the RAMP training. They wanted this pre-processed outputs in this format, like there would be chips folder, and the binary mask is the rasterized mask in 01, like normalized form. If we visit the grayscale labels folder, then we'll see that the rasterization is done perfectly. We can see all the building shapes clearly in it, and the labels files contains the GeoJSON files that are clipped for each of the individual tiles. So using this pre-processed data, we can fine-tune the RAMP pre-trained model, and Shaima will show this next. I would give the floor to her now. Thank you, everyone.
Thank you, Tassine. So I'm gonna share my screen. Okay. Okay, I'd like to start with the RAMP workflow. So after taking the pre-processed data from the scene, we would be doing putting it into the correct location into RAMP, and then moving into a data preparation stage before training the actual model, and then getting the checkpoints. We have everything provided in a guide in here for the actual running and the technical details, which I won't be going over through in this presentation for today. However, I'd like to jump into Google Colab, which we use to run and fine-tune the RAMP model. For the RAMP model, actually, we have a RAMP home that has all the folders in there. We're interested in RAMP code and RAMP data. Under RAMP data, we would have a training folder, which I would put the folders that I took from Tassine, the pre-processed folders over here. So I took them, I put them under binary masks, chips, and labels. And then we would go into running the actual data preparation code, which we will find over here under RAMP Code Colab. That's the notebook we use for data preparation. It's basically just to divide the data sets that we have into training and validation. So once we run this notebook, we will have another subset of folders for the validation, which is validation binary masks, validation chips, and validation labels. Once we're done with the data preparation stage, we would move into the actual fine-tuning of the RAMP model, and we did it using this notebook. So basically, we're using the RAMP code base provided by RAMP, and we modified it a little bit to be able to fit it inside our workflow for HotClip. When running this notebook, it reads a configuration file that has everything set with the directories and all the data augmentation and everything we tested out. And then it would show us at the end of the training, it would show us the curves for the training and validation loss and the accuracy as well. For the sake of the presentation, we just ran it on 10 epochs, and you would see this at the end. Basically, what we're looking for is a point of stability between the training and validation loss, and same for accuracy, with a small gap between the training and validation loss and accuracy to make sure that the experiments and we have good results. I will go ahead and run it in the background, but just to show you how things work, it will restart the kernel and get everything going. It takes like quite a time to run the model, so I'm not going to wait for that. However, I will go ahead and show you how I will grab the checkpoint file to give it to Tassine, which he will be doing the rest of the demo. So once we go again into the RAMP home, under RAMP data, the train, I will find it into the model checkpoints. I will grab it, and then I will be giving it to Tassine. I will check which one has the highest accuracy. Here we can see the accuracy numbers at the end. So this is the one with the highest accuracy. I'll grab it and give it to Tassine. And basically this ends the RAMP workflow for us. Getting the data from the pre-processing pipeline and moving with the RAMP, and then getting the checkpoints. I will just show you how it's running. For here, it shows the number of the epochs. So currently it's in epoch 1 out of 10, just for the sake of presentation. But as we said, we're not going to wait for the end of the pipeline. And I'll be giving the floor back to Tassine to continue the presentation. Thank you.
So from the RAMP model pre-training, we get a model checkpoint that we will use to predict on a test data set. So we have some data sets for some particular regions. So we're going to test on this particular region. It comes with a zoom level of 19, and then visualize the data with the help of QGIS later. But I'll first run the prediction script. For the prediction, we need to specify where the checkpoint is located. Currently, the checkpoint is in TensorFlow format. And then we need to specify where the test data is. We are expecting the data in PNG format, and it would be georeferenced because we will need this data to be in this format for post-processing operation. And then we need to specify where the prediction, like predicted images will go. So if we run this, at first it will take some time because loading a Keras model takes some time, what I've seen, due to the pre-trained model having a large size. For example, it was mentioned that the size is 121 megabyte. So we can see that the model prediction took 7 seconds, and for the georeferencing, it took another additional second. So in total, it's 8 seconds for a data set of size of 25 images. So the output predictions will go to this folder as specified. And we can see that some of the images have shapes in it. So the prediction ran successfully. We can visualize it later. But I will now show you how to perform the post-processing operations on it. So as explained by the previous speakers, we have kept two separate methods. Each of them has their own limitations and advantages. So I have kept both. Okay, so I will run the script. So it looks like the first operation vectorize that was implemented from scratch was, it ran very fast, almost instantaneously in less than a second. And the second function polygonize, it took around 11 seconds. Now, I have specified the output path, the path where the final GeoJSON file will go. So if you look at the file explorer, we have one with the suffix polygonize and another with the suffix vectorize. We can visualize these things in QGIS, but in order to judge their accuracy, like how good these vectorized polygons are, we need to compare them with the test data that we got. So as the test data is in PNG format, and we need the georeference images in order to visualize them in QGIS, we will perform another operation on the test data set. We'll just georeference these images and output some GeoTIF files. So as I specified, the output will go to /419. Here are the images. One more operation I did is I removed the fourth channel. Some of the images had a transparency channel in it, so that band got removed, and now we can see that it's black. So I will first add all the images, georeference images. So we can see the whole region, and then I will add the polygonized shapes. Yes. Let's check them one by one. So this is the output of the vectorize function. We actually ran a simplification algorithm on this, and previously it was a lot ragged shape. It is very irregular, the shape, and now it's much simpler. And if you look at the polygonized operation, then we can see that there are some more corners. And that's currently what we have done for the post-processing operation. I will give the floor to Gage now.
Thanks, Asin. So the last part is the conclusions, and I think that the team did a very good job in getting in 8 weeks where we are now. We took the RAMP model as the best performing model after selecting 6 other models or testing 6 other models that and even building our own model. We couldn't beat the accuracy and the precision of RAMP models. That's why we went into creating this pipeline for RAMP. And we also found in the course of the project this auto BEF algorithm that is also very helpful to polygonize and vectorize the images, so that everything kind of is packaged in one smooth operation to go from the raw images to polygons, and then the mapper will have a much easier task to identify the building footprints and correct the shapes that we created here. So we are not able to really make a building footprint like with crisp edges. The time was not sufficient for that, but at least we find that we have a very good agreement with detecting where the buildings are, so that at least the mapper won't have to start searching for the buildings, and correcting a building is much easier than finding a building and starting from scratch and digitizing the whole region. That's the effect of the purpose of this whole exercise, to make the life of the mapper easier in a large area. So here we're starting with training on 25 images, for which we have labels, and then we can upscale to the whole area of interest within the project area. So I think that was a very we made a lot of progress in this 8 weeks, and I think a very good job done by the team so far. So I'm very pleased to say that we have these 4 deliverables. We have the hotlib library. We have a fine-tuning script that takes the pre-trained RAMP results, but then is able to make regional adjustments. So that means also that this whole pipeline is scalable globally, so that you can test or create building footprints not only in the regions where RAMP has trained it, but you could go, for example, to a very remote area in Uganda and have the same operation or the same accuracy when you go to another area in Zimbabwe, for example. So it is not longer regional determined. Everything that is documented, so the code has very specific doc strings, and doc strings are all grabbed and exported into one repository. So there's a very quick way to verify what each function is doing and how it could be modified and used in HOT's own library or own processes. And the whole methodology is well documented, and all the steps and verifications are there. So with that, I think I have the outlook left, and that's where I hope to hand it over also to the discussion part, is that we try to make the process as human-friendly as we possibly can by using and introducing the use of machine learning and artificial intelligence, and that this kind of workflow can fit into HOT's operation. So that's, I think, where I would like to start having an open discussion or a question and answer session here at the end of the presentation, where we have presented the hotlib library and the pipeline. So I open the floor for question and answers. I saw that there were already some in the chat. Let me see if I can have some. But Omran, as we have been working over the 8 weeks together, any questions for the team?
Hey, Gilles, can you hear me?
Yes, I can hear you. Hello?
Yeah. As long as you can hear me, that's okay. No worries. I will manage my speakers soon. Yeah, thank you everyone, and I just want to add some couple items. After the post-processing, which Tahsin has presented, we could see that the buildings are not exactly aligned and they're not much suitable to take back into OSM. And that would be like what we're going to be doing after the challenge in hot OSM. And we'll be looking at having a perfect polygons that goes to OSM with like 90-degree angles. We're looking also at supporting round buildings to detect like round buildings and expand that into other features. As of questions that like actually came from other channels, why we test this only in 5 different regions and why we selected those regions. 5 regions was just an example because we needed to see how the training of the models will be performing in different regions. So we selected those from open aerial map in like the 94 priority countries. Some of them are in Africa, others in Latin America and in Asia. But that would be the scenario for any new training dataset that would be created by any mapper. And then from there, it will take the training and fine tuning in a live environment. We have a question about the augmentation, why we didn't do more like augmentation on the data. We're limited with somehow the live prediction that we were trying to do and the live training, because we'll be bringing the ability for OSM communities in order to create their own models for their specific region, rather than having a general model that works over the whole globe, which in some regions doesn't perform well. And I think we faced already that challenge in region number 5, because it was like a very crowded area where buildings are very close to each other and we couldn't somehow have a good results. I think the accuracy were around 80. Exactly, it's something in compare with like 95, 97 in other areas. Yeah, like that was my intro, like my contribution to the presentation. Open for more questions, or even from the community on LinkedIn. I'm tracking the comments there, or from inside Zoom here.
Yeah, I just would like to tap into your comment about region 5. I don't have an image for region 5, but for the audience listening, it's a SLAM area in, I think it is Mexico City, or a comparable environment where models are struggling to detect the difference between the road, the roofs, and the houses themselves, because there is not enough variation, or there is the models can't distinguish anymore what is a building and what is not a building. And that's again what Omran was saying, like why not using one global model, but why using this specific area? This is exactly the reason. So in the next phase, and hopefully in the next the next phase of this development, is that particular trained models could be selected as the second pass. So this is a general pass, and you see that your accuracy is dropping under 80. So you could then start using a model that is more fitted or more tuned to this kind of more complex situation. So in an area with little houses, or with houses that are well structured, the models are performing very, very well. But in these kind of complicated cases, machine learning has just its limitations. So that was my point here. So yeah, that was what Deepali is saying in the chat here as well, that that XBooks, as one of the models that we tried, was performing well, but not in the more difficult parts, and that was then also due to how much elements and how many images we could feed into it. Prompt has just many more images that you could make use of, and with Xbox we should have created that library ourselves, so we wouldn't have the time to do that. Any more comments from the audience or questions? I don't see any questions, no hands raised. So I would kind of then ask a question myself to the team. What would be your recommendation for Hot OSM to focus on? What would be the best area where the model could be improved on? The mic is open, so someone wants to take that question?
Yeah, in case of dense areas or areas with a cluster of buildings, so there is more training data necessary, I think, for fine-tuning the model. So this is the dense areas are also in the RAMP model the most critical. Most critical part.
Then, yeah, I completely agree there. But, thinking about how more images could be brought in, because we are already in RAMP using, I think it is 80 gigabytes of satellite images pre-selected from the SpaceNet 6 repository. Are there, and where we are training on are the drone data set that's from the Open Area Map project. So where would we find those images? Or Omran, perhaps a question back to you. Do you think that the drone images are of a good enough quality to perform this kind of actions on?
Run that again by me, please.
So we use RAMP, which has satellite image, high resolution satellite imaging, and that's the train model. Then we pre-train on, or you kind of use the input for our predictions as drone images or the Open Area Map resolution images. Do you think there is a disconnect between those two?
I don't see any disconnection between both of them. Actually, so far, RAMP has produced the best quality among what we did during the last 2 months, 8 weeks, and seems like we're also open like for other models to jump in when we design and implement our tool fair. When we have the RAMP, we will like make sure that design would include also other models that can be included later. But so far, this is the best quality we're getting. This is what we have in hands, and that's like only the beginning of having more models predicting features, not only buildings, even like others. Based on satellite imageries, I somehow like see another challenge coming maybe in the next year of even leveraging street imageries. There are some open street imageries that can be also used to detect much more features beside the polygons. from like the aerial vision, like even from street imageries. That might be also one of the new challenges we face soon.
Yeah, exactly. It's all about what kind of data can you put in, and I completely agree with the RAMP model being the most accurate, knowing that the SpaceNet is behind it. You're only limited to what they train on, so they don't provide more. If there is not a SpaceNet 7 or a SpaceNet 8 with new images, then you're stuck with the SpaceNet 6, and you can't really bring in more. But no, the RAMP does a good job, and I think with the drone images that coming in from the Open Area Map project, you have a good coverage. Now, the only question here is, what are you doing when the drone images are not available?
So far, we don't have an alternative solution because like other imageries are not licensed to be used in like machine learning algorithms and the trained models. If we reach a point where we can leverage open source imageries and if that's available for OSM, that would be amazing. That would be a cover for the whole world. The quality of the images will be also another challenge currently within the 5 or regions we tried. Also other imageries that are available in open aerial imagery are like high quality. Sometimes it's like 10 centimeters or 2 centimeters per pixel. While the ones available like open source, the available for OSM are somehow like 30 to 50 centimeters quality. That we need maybe to check if RAMP would be performing there, but license is one of the challenges facing that experiment. Also, like, I know that's not exactly related to the challenge, but this is what in humanitarian OpenStreetMap vision to run drones in the priority countries. So we have like other teams who are working on producing drone devices with a low cost that can run in any location and then process those imageries, and then we would be able to use them in the same tool using the same technique currently we're having with Omdina.
Exactly,
So,
and then you can do an before and after, so you can more directly point to where aid is needed and to detect those areas that are hit most.
indeed, yeah, like you get the point intuitively. That's amazing.
All right, I'm seeing that we are still kind of on the hour, 5 minutes left on this presentation. So if there are any questions from the audience, I am more than happy to take them and direct them to someone in the team.
One more suggestion in terms of models that could potentially be tried in the future is fast RCNN model. I know we didn't get to try that from what I know, but there's supposedly a more accurate, it has better accuracy, and it's also faster in semantic classification. I mean, semantic segmentation. So, yeah.
I think we are mentioning this in the report as well, and I think it's a very good alternative. It's always good to have the second option. I thought there was only one thing that it was harder to set up or to integrate. That was one of the reasons that we dropped it out or didn't run it in parallel with RAMP, because we only had those 8 weeks to run it. It's a very good alternative or a second option. Sina, I see that. Yeah, of course we can pick up the answers or questions after the call in the comments of the event. So if there are any other questions or remarks or suggestions, then please use the comment in LinkedIn, and we come back to you on those after the call. if I don't see any here, it's very hard to do that. So I think with that, Omran, I'm very happy that yeah, we came to this conclusion here at the collaboration between Omdema and HOT. I hope that it was as pleasant for you as it was for us to work together. And I think I'll speak on behalf of the whole team that it was very nice working in this challenge together.
Thank you, Gis. It's impressive. It's amazing, the diversity within the team, the experience of looking into the problem from like a different perspective, and how is that associated with the distribution of the team across the globe, 12 time zones, like 15 countries. And highly appreciate how the team were able to manage the time zones. Someone is attending a call 5 a.m. in his time, and others are attending the call also like midnight. That's cool. And thank you for ruining my Saturdays for the recent 8 weeks.
That's the thing in Omdema. That's how you run, and that's I think how most things are going this well in the project. That when you have that level of commitment, and then you get this kind of result. So yes, it's all kudos to the team and well done.
Hi, everyone. I just also wanted to stretch out a huge thank you from everyone in HOT. It's going to be so interesting to follow up also. And everyone out there watching this also, it's quite technical, but we will also work on creating a bridge between that technical language and and the humanitarian impact that we're seeking to find here. So thank you so much for this presentation also. Geez, everyone.
All right. Thank you, Sine. Yeah, I'm looking forward to a continuation. Hopefully there is a second start, and I think there is definitely room for improvement, but for a first pass on detecting buildings with imaging, I think the team did exceptionally well. So I think with those words, I'm more than happy to close the call. If there are no other suggestions, again, team, well done. 8 amazing weeks and very nice results for a challenge like this. So thank you.
Thank you.
Thank you. See you.
Thank you.
Bye.
Thank you. Bye.
Bye-bye.
Thank you. Bye.